our lecture on Thursday. Okay, we've started. So today there's quite a bit to teach. So we are going to look into combined loading. Okay, so the topic is still the same, but I'm going to be more specific. We're still identifying bending moment, shear forces, and torque. Then after that, we're going to calculate normal and shearing stress, and then we're going to construct. Okay, we're going to construct the elements. Okay. So the structure that we are looking at more specifically now is we are looking at stresses that is under combined loading. Okay, so we have not finished this example yet. So where we stop, or let me quickly recap. Like what I mentioned before, this is a 3D problem, and a piece of paper is a 2D world. Okay, so I'm teaching you guys a protocol on how to identify a moment, shearing force, and a torque by viewing the structures from different orientation. So what we have done, the first one we have done is we have looked at the stresses, okay, the force, the load applied in the XY plane. Okay, so we have identified in our XY plane we have moment about Z and axial load in the x-axis. Okay, so a thing to consider, very important with these rules that I'm teaching, we don't analyze those forces that are either a dot or a cross. So let me elaborate. If this is a dot, this is a cross, don't analyze them. Okay, we only analyze them if it's an arrow like this. Okay, the rest don't analyze them at all. We have to construct in a view in another orientation so that the dot and the crosses will look at an arrow. Okay, I know it's a lot. Okay, what I'm saying, like, you have to remember. So the next view, so over here when we were in XY plane, we have identified there's a moment in the Z direction over here, and then we have a PX. Okay, and then there's nothing else to analyze. Okay, then we look at another view. Okay, so this view we have not finished analyzing yet. We were still analyzing it. Okay, so what we did is we are identifying the moment about Y. So as we know, moment is equal to force times distance. Okay, so this is the result, the 900 pound-inch. Okay, in the orientation that looks in a clockwise direction. Okay, so element H is equal to 0, element K is compression. We have to make that decision now, or we have to analyze now, then it gets less confusing. And always bear in mind how the shearing stress is distributed and how the normal stress has been distributed. Okay, you have to visualize this. Okay, so what do I mean by that? Always remember, in the shearing stress, right, at the centroid, the shearing stress will be at maximum, right, and then due to bending moment, the normal stress at the centroid, okay, is equal to 0. Okay, so you have to remember how the pattern is constructed, or the load is distributed. Okay, so we finish off, last lecture we found moment Y at element H and K, and then we also wrote this down, the element H is 0 because element H is at the centroid, element K is in compression. Why is it in compression? Because element K is here and compression is the head of the arrow. Okay, so we are going to do the next bit. Okay, we are not done. Now we are going to look at summation about forces. Okay, summation about forces. Positive is going upwards, Z. Okay, so we're going to add all the forces in the Z direction going upwards based on the orientation we look at is positive. Okay, so upwards is positive. Okay, so this will be 150 plus by 50 minus by 200, right? So this is happen to be equal to 0 pounds. Okay, happen to be. Okay, so with that, anything else to analyze? The answer is no. Okay, then we have to draw the third view. Okay, so all the analysis is best to be carried out in 3 planes. Okay, so the first plane that we have done, as I mentioned before, this is the XY plane, right? Then the next one that we have just done, this is the XZ plane, all right? And then another plane that you have to check, okay, you have to check is the next last plane that we have to check is the YZ plane. Okay, so YZ plane. Okay, then this is our rotation about X. Okay, so now we're going to construct this structure, right, on YZ plane. And there are things I'm going to remind you. Mira, because the sum of the vertical plane is 0, there's no shear force element. You are absolutely right. Okay. Yeah, Mina, you're absolutely right. If this is not equal to 0, then we're going to have I'm tongue tight now. We're going to have a shearing stress induced by the shearing force. Okay. All right. So the next thing that we're going to focus now is we're going to focus on that plane now, which is our YZ plane. Okay. I think you have done a bit of this in 2PO4, where you have force vector acting on thrust. Am I right? Anyone can recall? I've seen Dr. Koshi's notes on 2P. Am I right? Anyone? That you guys have been dealing with 3D stresses. I mean 3D vectors, but all these 3D vectors, you guys are focusing on thrust analysis. Okay. So you've done a bit of this. I don't think you are surprised by what I'm doing now. I like to think they are not surprised. Okay. So this will have. So we're being on the YZ plane now. Okay. So there is 10. So 3, 6, 9, 10. Okay. Then again, now our neutral axis. So let me consider. So this is a hidden feature. Okay. Right. And then over here, this is our centroid or neutral axis. Okay, this is our neutral. Yeah, call it centroid or neutral axis. I forget. Neutral axis. Wait, I now forget whether I call it neutral axis or centroid. Yeah. Let me go back a slide. What did I call it? I can't remember now. Neutral axis. Sorry. Okay. So this is our neutral axis, right? And then we construct our element. Okay, so we draw element. So we have one element over here. We have one element over here. So this is our element K. And then over here is our element H. Okay. Then we put in our forces. So we have a 150 pounds. By the way, I've uploaded images on Avenue to Learn that I'll be using for today's lecture. So if you do have time, or try to download them while watching the lecture at the same time, if you can. Okay. Then over here we have 200 pounds, right? And then the other side, right? We have 150 pounds, and we have 50 pounds. Now, if you have two forces, right? Don't just. Is it possible to draw two forces superimposed one another? So what I usually write to tell me that I have two forces, I put a comma. Okay, one is 150 pounds, one is 50 pounds. Okay, so now do not analyze anything that's a dot or a cross. We don't analyze that. So now what we are going to see now is we're going to analyze the 200 pounds, and then over here we have our 150 and 50 pounds. Okay, so over here we have do our summation about Z already. Okay, we have do our force summation about Z, and we realize that it's equal to 0. If you want to do it again, fine. Okay, but you don't waste time. You know, if that, because when you form the equation, it look exactly the same. Okay, so don't waste time. Move on. Now, the thing that's interesting now is the 200 pounds, right, is creating it has a certain distance away from the neutral axis. Okay, let me elaborate. Okay, let me elaborate. So what I mean by that is relative to the neutral axis, right? We have a distance from here to here, right? We have a distance from here to here, and this distance is 10 inches. Yeah, this distance is 10 inches. Okay. Now the thing is this. What is this 10 inches with a perpendicular, I mean, this 100 and 200 pounds and a perpendicular distance of 10 inches? What is it going to generate? Anyone? Is it a force or a moment?
To generate torsion.
Generate torsion. Why?
Because it's at a distance from the neutral axis.
Yeah, but moment also can be a distance from the neutral axis.
The neutral axis doesn't change shape.
Huh?
The neutral axis doesn't change shape, like not a U or not a smiley face or a frowny face type thing.
Yeah, there you go. Okay, well done. Okay, right. So if you look, so again, go back to what? Looking at deformation, right? I always elaborate. Look, okay. So by looking at deformation, how this thing will deform, okay, it will rotate. Okay, I'm going to use a different color. It will rotate this way. Come on, Eugene, seriously. Okay, so this is our deformation. The main focus over here is we have to look at how the neutral axis has been deformed. I repeat again. Okay, I'm going to write down how the neutral axis is deformed. Okay. Right. Some of you might say, Eugene, you know, you draw it straight. Okay, fine. If you don't want to draw it straight, you can draw it bend a bit. I'm okay with that. Okay, you want to draw this way, fine. Right? You want to draw this way, I have no problem about that. But the most important thing is the location of element H and is the location of element K. Anyone can tell me why? Anyone can tell me why? Okay, no doubt the arm. Okay, the arm, this one that's carrying the 200-pound load, it can be bending. Okay, but it's fine. Okay, but we only focus on where the neutral axis is and relative from the neutral axis to the element. Why is that? Anyone? And the answer is simple, because what are we interested is the what? Stresses on element H and K. This is the primary reason why we have to construct where the element is and why we have to construct where the neutral axis is. Okay, you have to put this down first, right? Before you talk about what is a torque, what is a moment, okay, and what is a shear force under loading or acting on the elements. Okay, so now you know that, right? Now you know that. So we are going to calculate the torque. Okay, so torque. Okay, so now we know torque is equal to force times radius. All right. How to identify the top is the neutral axis